Right, so let's have a look at ways of imaging the brain. So this is something that again is on the advanced information for psychology, and this is for biopsychology. And this is a topic I think is actually a lot nicer than it looks like. It looks very threatening and menacing from the outside, but actually it's very simple. And the reason it's very simple is because the evaluation is really easy to get your head around. It's not as required, it's not as discursive or as complicated or as other topics. For example, you're not required to bring in issues and debates or anything like that. It's very much what it says on the tin with the evaluation here. So let's have a look. So there's four ways of imaging the brain you need to know. fMRIs, EEGs, ERPs, and postmortems, which is a lot of letters that probably don't mean too much, but we'll go through each of them in turn. fMRIs, functional magnetic resonance imaging, not to be confused with SMRIs, which is structural magnetic resonance imaging, but functional is the clue. We're looking at brain function, brain activity. We're not looking at the structure of the brain. We're looking at what it's doing, its actual activity. fMRIs measure brain activity through changes in blood oxygenation in the brain. So when the brain is active, those areas of the brain that are being used will demand more oxygen. And because they demand more oxygen to work, they need more energy. That requires greater blood flow to that region of the brain. So more oxygenated blood will travel to those regions of the brain to meet the increased demands for as long as that region of the brain needs the energy to complete the task it's trying to complete. And this is called the hemodynamic response. So hemo references blood. So it just means a dynamic, active variable blood response to within the brain based on what it needs at any given moment. So oxygenated hemoglobin. Hemoglobin is something that's in your blood that carries oxygen molecules through your body to provide oxygen to cells. And when hemoglobin is oxygenated, its magnetic properties are different to deoxygenated hemoglobin. And it's this particular property of hemoglobin, which is what allows fMRIs to track the variation in blood oxygenation through the brain. So the fMRI, because it's magnetic, can distinguish between oxygenated and deoxygenated blood as it travels through the brain. But because you can imagine that when the brain area becomes active and it needs blood flow, it takes time for the body to transport that blood to that region of the brain and for it to access it, which means that activity has a bit of a time lag. It's 1 to 4 seconds on average after activity begins. The oxygenated blood arrives. But it is quite spatially accurate. So fMRIs are accurate within 1 or 2 millimeters. And that is your evaluation right there. I've already touched on it. So really high spatial resolution. You can resolve activity to within 1 or 2 millimeters, which compares favorably to EEGs we'll see next. It's risk-free because participants or patients don't have to have it's non-invasive. So there's no nothing's being attached to the scalp. There's no element of trying to dig inside someone's brain. And that makes it easy to administer as well. So it's quick and easy to administer, no risk to the patient, non-invasive, nothing is going inside the patient's body. That's what we mean by that. But as I said, temporal resolution is quite low. So it takes 1 to 4 seconds for the blood to reach the region of the brain that's become active, which means you see the activity quite a while after it's actually begun. And also you may have surmised that we're not measuring activity directly. We're not looking at the activity of individual neurons here. We're just looking at the activity at the level of blood flow, oxygenated blood flow through a region of the brain in response to that neural activation. So it's not a direct measure of brain activity. And they would be your negative. So 4 really nice simple points here. You would never be asked a 16 marker to discuss one or even two ways of measuring the brain, it'd be much more likely you just get a 6 marketers discuss ways of measuring investigating the brain. So your evaluation doesn't have to be as in-depth because you're able to draw on multiple points from multiple methods. And an interesting high-level point would be perhaps to make the comparison. So I've said here that the spatial resolution is high compared to EEGs, which we'll look at next. And that would be some quite high-level evaluation to bring in, where you're making those links between and across different ways of measuring the brain. EEGs, electroencephalograms. Try and say that 3 times really fast. But EEGs, unlike fMRIs, these do measure electrical activity directly in the brain by using electrodes positioned across the scalp. So you still can't look at the activity of individual neurons. There is a way of doing that, but it's not something that's covered by the spec, so I won't dip into it today. But you measure activation in different states generally. So you're just comparing patient's brain activity when they're awake compared to when they're asleep, or when they're calm compared to when they're aroused. And it has diagnostic capability as well. You can use it to diagnose Alzheimer's or epilepsy, so particular neural disorders. And that kind of leads nicely into the evaluation. So because it has good practical use, because you can use it in a diagnostic way, so it can help people access treatment sooner, because they can use these methods to diagnose disorders like epilepsy, and minimize, and because they can then access treatment, that can minimize the disruption to their everyday life. It's non-invasive again, so it doesn't go inside the brain in any way or inside the patient's body. So there's no long-term risk to participants at all. Very high temporal resolution, so it's very, very accurate temporally. So you can resolve activation to within on an order of milliseconds rather than seconds in terms of looking at when it occurs. Poor spatial resolution, though. It's very hard to localize and pin down where the activation is occurring. Rather, EEGs give a more distributed, holistic, to use that word, you know, from issues and debates, a holistic view of activation across the whole brain, so broad changes in activity rather than specific regions of the brain. But it is extremely uncomfortable, and that is a genuine issue with this method, and I can vouch for that because I've worn one of these EEG nets. They are extremely uncomfortable because if there's any kind of relative movement across your head of the electrodes, it blurs the image. Imagine it is like trying to take a photograph with your phone while moving your phone. It's going to blur the image. And likewise, if the electrode's moving across your head as the activation's occurring, it's going to blur the image as a result, blur the picture of the activity. So it has to be held extremely tightly across your head, and there's a really tight strap across the chin which pushes up below your chin. And if you push up there for a long time, you'll find you start to feel quite nauseous. So this does make the participant feel sick, and because they have to stay still as well, it's just very uncomfortable. So that is a serious downside, unlike an fMRI where a patient's quite passive, just lying inside an fMRI scanner. These are very different. And they lead nicely to ERPs, because ERPs still use electroencephalograms, but they're just a specific way of applying it to address some of the shortcomings. So we said that you can only look at activity in certain states. Okay. And you can't there's poor spatial resolution because there's so much activation going on in the brain. The brain's constantly firing, neurons constantly going, so it's hard to localize and pin down that activity. ERPs try and address this by taking an EEG and looking at changes in activity in response to specific events rather than looking at just the brain in particular states. ERPs do this by conducting a vast number of trials to try and filter out the extraneous brain activity, the unwanted brain activity. Because there is so much noise there, you have to do hundreds or even thousands of trials to filter it out. So when I wore an EEG, the experiment I was participating in, I was having to listen to audible tones, and it was looking at the brain's activity in response to those tones. But you can't just do it once or twice. I had to listen to the same tones hundreds of times each so that the random activation going on in my brain could be averaged out, which is problematic, and we'll come on to that. But because you're able to filter that brain activity out, it does allow you to identify specific neural responses to specific events. There's two types of ERPs. Cognitive ones occur around 100 milliseconds after a stimulus or event, or 100 milliseconds plus, I should say. Sensory ERPs, the response is less than 100 milliseconds after the stimulus event, because you track the change in the in activation in the brain in a particular region. So you're able to see where that initial change in activation occurs, deviates from the normal. If it's below 100 milliseconds, they're sensory ERPs. They're much more automatic, reflexive. If they're cognitive ERPs, they occur post 100 milliseconds, because generally it's reflecting some kind of deeper processing. If you think of the cognitive approach, the mind's like a computer. So that the longer processing time reflects some kind of information processing that's going on. So this is what an ERP response would look like. You can see this is a sensory ERP, because if you have a look here, the first response is within 100 milliseconds after the image. So let's just say this is a response to a participant being shown an image of a spider, a tarantula. I hate those things. So we're looking at someone's response, neural response to something they fear. So the initial response occurs within 100 milliseconds because it's an automatic sensory response. And you can see there's actually three responses here. So we've got the one just before 100 milliseconds. We've got another one at around 150 milliseconds. And we have another response at 250. And these kind of patterns of what ERPs look like, event-related potential. So we're looking at changes in the electrical activity of the brain. So over here, the brain's becoming more positively charged. And over here, there's more of a negative charge. And eventually, the signal will normalize and go back to its normal level. I just wanted to give you a visual picture of what an ERP is doing. It's looking at the change in the electrical potential of the brain in response to a specific event or stimulus over a time period. So we can look at the time course of that change in activation. Okay. Evaluation. Address a lot of the issues with EEGs. So the EEGs lack that spatial resolution. They can only look at the brain, compare different states of the brain, like I said, the cycle of sleep, or looking at epileptic patients, for example, during a seizure. This goes beyond that. So we're no longer looking at just the states of the brain, different states. We can look at the brain in response to specific events. And because of what I showed you here, really high temporal resolution, we can resolve details or specific responses down to a few milliseconds, and we can chart this in great detail because you're doing it over so many trials. So it's the large number of trials, doing hundreds of thousands of trials, which allow you to do this. You can filter out away all of the noise confidently to be left what is the true response to the stimulus you're showing the patient. But that is the downside, that you require lots of trials to average out the noise, at least hundreds, which is going to lead participants to become tired, distracted, or feeling ill from the EEG net that they've been wearing. It could also lead to the participants sort of adjusting their neural responses, adjusting to the stimulus you're giving them, because there's so many trials. So if I was showing a tarantula, likely the first time you show it, I'm likely to have a much stronger response than the 500th time you show it to me, because I've adjusted, I've acclimatized. So the response might become weaker over time, which then makes it harder to average out the noise, because you're having to adjust as well for the fact that the response you're actually looking for is changing over time. So there are a few drawbacks with ERPs, but generally they're much more useful and effective than just a raw EEG signal. Last one is post-mortems, probably the simplest. It's a structural analysis of the patient's brain after death. So if the patient had a rare disorder during life or an unexplained behavior, by doing a post-mortem on their brain, you can see if there's any differences in brain structure. If there are differences in brain structure, that could suggest that those regions were in some way deficient or abnormal, that may have then been responsible for the behavior or symptoms they were showing during their life. So if you think of Phineas Gage, when he had his that pole that went through his frontal lobe, by doing a post-mortem and seeing the differences in his structure compared to a normal brain, you can then understand which regions of the brain were responsible for his abnormal behavior. And because you're able to act on freely on a brain that's dead, gives you much opportunity for much more detailed anatomical study than any other measure that we've discussed so far. You can look into the deep inner regions of the brain, whereas ERPs and EEGs are only giving you the surface activation. They're not probing deep into the brain. So you can look at deeper structures there. But you're not able to look at activation or activity. You can only make inferences about possible causal links. So there is a correlation causation issue. You can't confidently say, like you could with an ERP, this region of the brain is responsible for this particular function or this activation, or it's associated with this activation. You can only say, well, this region of the brain looks different than what it should. The patient had these symptoms. They may be linked. They may not be. You can't make the kind of firm conclusions you'd like to. Informed consent may be an issue. If you've got someone who's had a particularly rare disorder, it may be scientifically valuable to investigate their brain with a post-mortem, but they may not have given consent for it when they're alive, or their family may not have done. And if they've got particularly rare disorders, they may not be able to give consent either. So even if you could have asked them, they wouldn't have been able to. And as I said as well, the fact that you can't look at directly at activity, only structure, is a problem. With an MRI, as I said, there's functional MRIs which look at activity. There's also structural MRIs which are able to give you an anatomical view of the brain. But post-mortems, obviously, because the brain is inert, it's dead, you can't look at activation in that way. So that covers all four ways of imaging the brain that you need to know. You may have been taught others. There's PET scans, positron emission topography. I mentioned you can take direct recordings of single neurons. They're called single cell recordings. You can also do multi-cell recordings. So any other ways of imaging the brain you may have learned are valid and a useful evaluation when comparing them to the ones I've shown you today. But just be mindful that the ones I've shown you today are the only ones you need to know for the exam. Everything else is evaluation or not necessarily expected content. But the four I showed you today are named on the specification and are named on the advanced information. You do need to know them. But just because you know, if you know others, don't be discouraged from bringing them in if you do know them. Okay, so just wanted to make that clear. But thank you all for watching. So that's the end of this week's sessions. Reminder that I have the drop-in on Saturday mornings at 10:30. I know it's an awkward time, but it's the only time that's free in my week, really, where I can set aside an hour just to answer any questions you have. But if you do have any questions, please come along prepared. With them, I'm happy to have a chat and answer them, or if you want to talk about the exam or anything, absolutely fine. Thank you for watching again, and hopefully it's been helpful, and talk to you next time.